Thank Thank you. Thank you very much. Thank you to the organizers for this wonderful conference and for inviting me to speak. I'm really very honored. I'd like to tell you today about, as the title says, some properties of a variant of Lie n. Um, and first of all, I have to start by telling you about the free Lie algebra. So this variant is a variant of the representation of Sn on the free Lie algebra. So I'll start with that and tell you what the classical Lie n module is. And then I'll go through some properties. And then I'll introduce this variant and go through properties of that as well. And so the thing that I want to highlight here is that I stumbled on this variant doing purely symmetric function manipulations, but it's quite remarkable. It seems to have a counterpart for every property you can think of the classical Lie n representation. Okay, so and everything will be over the complex numbers. So let me start with the free Lie algebra. So I have a vector space of dimension n with basis a1 through an. If you like combinatorics on words, you can think of this as the alphabet. And then the tensor algebra over V consists of words of finite length in the alphabet A. And the free Lie algebra is just simply the smallest subalgebra of the tensor algebra that contains V and is closed under this bracket operation. So U bracket V is UV minus VU. So this is a Lie bracket, so it makes it into a Lie algebra. So that means I have anti-symmetry and I have the Jacobi identity. All right. So this has been very well studied, well, from a long time ago, actually, from probably the 30s, but more recently in the late 80s, 90s, there was a big flurry of activity about the free Lie algebra. There was a big resurgence. So this free Lie algebra has a multi-grading, but the piece of the free Lie algebra I'm interested in is the multilinear component, so the graded piece corresponding to all ones, which you can think of as the subspace spanned by all possible bracketings of n distinct letters that, of course, we're going to take to be 1 through n. It carries an Sn action, so this is the symmetric group Sn, and I'm going to call this representation Lie subscript n. Right, so the classical Lie, you'll see, I will try to always write in blue. So the first theorem is that a basis for Lie n is the set of left-normed bracketings. Garcia calls these left combs, right? So this consists of bracketings of permutations in Sn of the form you take the bracket of sigma 1 with sigma 2, and then you take the bracket of that with sigma 3, and so on. So your last bracket is sigma of n, but you want sigma of 1 to equal 1. Okay, so because of this theorem, we know that Lie n has dimension n minus 1 factorial. So Sn acts by replacement of letters, as I said. So I just want to do two small examples. So when n is 2, Lie 2 is the span of the bracket of 1 with 2. So that's the linear combination of these two permutations, 1, 2 minus 2, 1. And how does the transposition 1, 2 act? Well, it just flips 1 and 2. So because of the anti-symmetry of the Lie bracket, what the bracket of 1 with 2 gets sent to minus the bracket of 1 with 2. So S2 acts like the sign representation. N equals 3 is a little more interesting. So now I have two possible bracketings with starting with 1 on the extreme left. Right. So this, if I wrote these out as permutations, so if I expanded the brackets, this is what I would get, these two linear combinations. And again, how does 1, 2 act? So I'm just switching 1 and 2. So it sends the first basis element to its negative, and it sends the second one to something else where the 1 is no longer in the leftmost position, but you can straighten it out using the Jacobi identity, and this is what you get. So if you calculate the trace, you get -1 + 1, which is 0. So if you go through this calculation for the 3 cycle, you will get a trace of -1, which allows you to conclude that S3 acts like the two-dimensional irreducible indexed by the partition 2, 1. Okay, so the next few slides are just actually more to familiarize yourself with the notation that I'm going to be using and the context in which it will appear. So GLVs, the group of invertible linear transformations of a vector space V. Symmetric functions in M variables are characters of polynomial representations of GLM. They're also, via the Frobenius characteristic map, in one-to-one correspondence with representations of the symmetric group Sn. Plethism, which I'll be a little more careful about the definition in a minute, but plethism of symmetric functions corresponds to composition of GLV representations on the one hand. I won't be saying very much about Riesz products, so I'll just leave it at that here. Okay, and this, fortunately, Sylvie has already more or less gone over, and Richard also yesterday. So partitions of n, these are integer partitions of n. My notation for the number of parts of lambda will be L of lambda. PR and P lambda are the power sum symmetric functions. S lambda is the Schur function. So again, on the one hand, S lambda in M variables is the character of a GLM irreducible Weyl module indexed by lambda. But S lambda for a partition lambda of n is the Frobenius characteristic of the Sn irreducible Specht module indexed by lambda. Okay, and then we'll be seeing a lot of these symmetric and exterior powers. So I want to say a little bit about that. So the homogeneous symmetric function Hn, on the one hand, it's the Frobenius characteristic of the trivial representation of Sn. But on the other hand, it's also the character of GLV acting on the nth symmetric power of V. And likewise, the elementary symmetric function corresponds to the sign representation of Sn, but it's also the character of GLV acting on the nth exterior power of V. H1 to the power n is the characteristic of the regular representation of Sn, and it's also the character of GLV acting on the nth tensor power of V. And then finally, another thing we'll be seeing a lot of is the involution omega that sends Hn to En, and it corresponds to tensoring with the sign representation. Okay, so this is just if you haven't seen this recently or ever, for GLV characters, if you take a diagonal matrix, here's how it's going to act on the kth tensor power of V, just diagonally. So you can actually very concretely compute this, and you'll see that it's H1 to the K. Right? Similarly, if you computed the trace of this diagonal matrix on the kth symmetric power, you will end up getting the homogeneous symmetric function HK, and on the kth exterior power, you'll end up getting the elementary symmetric function EK. Okay, so plethism and plethistic inverses. I'll just define plethism the way it's defined in McDonald. If I take G, a function G, that's a non-negative sum of monomials, and this is the multiset of monomials in G, x to the alpha 1, x to the alpha 2, then F plethism with G, so I'm using square brackets for plethism, is simply the function that you get by taking the monomials in G and substituting them for the variables in F. Right? This is not usually a good way to compute plethism. Symmetric functions f and g are plathistic inverses if f plathism with g is g plathism with f is H1. So H1 is the identity for plathism. Okay, so another thing you'll be seeing a lot of is things like H bracket with F. So I just wanted to say a little bit about how to decode that. So I'm going to write capital H for the sum of all the homogeneous metric functions starting at H0, which is 1, and similarly capital E. So if F is a series of symmetric functions, now starting at degree 1, it's the GLV character, it's not degree 1, sorry. It's the GLV character on a vector space W that's a direct sum of WI's. So the Fi is supposed to be the character on Wi. Then when I write H square brackets F, which really is a computable plathism, it's the GLV character of the symmetric algebra on W. And similarly, E square brackets F is the GLV character on the exterior algebra of W. So we can refine this a little bit and say that if lambda is a partition with mi parts equal to I, then we can define H subscript lambda plathism of F to be the character of this particular graded piece of the symmetric algebra. So you take the mi symmetric power of Wi and tensor all those together. And again, similarly for the exterior algebra. And finally, 1 over 1 minus H1 expanded as a geometric series is the GLV character on the full tensor algebra. Okay, so very little bit about the regular representation of a finite group, but especially in the context of the symmetric group, because that's what this talk is about. So the regular representation of Sn decomposes into irreducibles indexed by partitions lambda of n, and translated into symmetric functions, it says h1 to the power n is a sum of Schur functions S lambda, where the multiplicity is F lambda, the number of standard Young tableau of shape lambda. So one of the things that I find rather remarkable is the many different ways in which you can decompose the regular representation of Sn. And actually this is more generally true for the Coxeter groups, and they're all very interesting. So here's one way that has been very much studied. So Cn is going to be the cyclic subgroup of Sn generated by the long cycle, 1, 2 up to n, and omega n will always be a primitive nth root of unity. The irreducible representations of Cn are all one-dimensional, and the way you get them is by raising omega n to the power k as k goes from 1 through n and sending the generator sigma to omega n to the power k. So as a decomposition of a group, the regular representation of the cyclic group decomposes like this into n pieces, from which you immediately get, by inducing up, you get a decomposition of the regular representation of Sn into n pieces. And this is a very famous decomposition that has a lot of interesting combinatorics associated with it. Okay, so back to the free Lie algebra and the Lie module. So why am I talking about all this? Well, in 1974, Klyatko actually showed that the induced representation that you get when you induce the primitive nth root of unity from Cn to Sn is that representation is isomorphic to the representation of the free Lie algebra on n generators, the representation that I called Lie n. So that was pretty amazing. But already before that, a long time before that, Angeline Brandt in 1944 had computed the Frobenius characteristic. So, if they had recognized this this expression. So let me say something here. So this is 1 over n, sum is over divisors of n, mu of d is the number theoretic Möbius function, and this is pd to the n over d. It's actually not hard to show that this is the Frobenius characteristic of this induced representation. So this also follows by Schur-Weil duality from this theorem of Angeline Brandt. So there are lots of things that you can immediately deduce from this, which you could also deduce from the basis I talked about for the free Lie algebra. Lie n restricts to the regular representation of Sn minus 1. I also want to define something called a higher Lie module. So this is an H lambda of Lie for a partition lambda of n with mi parts equal to I. So you should take this as a symmetric function definition now. This is defined to be hm1 plethism with Lie1, hm2 plethism with Lie2, and multiply everything out. Right? So here's an example. For the partition 4, 3, 3, 2, I have h1 of Lie4 times h2 of Lie3 times h1 of Lie2. Okay, so 4 appears with multiplicity 1, 3 appears with multiplicity 2, and 2 appears with multiplicity 1. So in this small example, you can actually compute this by hand. Okay, so the next big fact here is a theorem of Thrall. I'm going to write Lie for the series of Lie n modules. And Thrall's theorem says, it essentially says this plethistic identity, that the plethism of the series H with the series Lie is the reciprocal of 1 minus H1. So if you unravel that, what you're getting is that H1 to the n is the sum over partitions lambda of n of these higher Lie modules, H lambda of Lie. So this is a different decomposition of the regular representation, again indexed by partitions of n. And the components are now these higher Lie modules. So it's always useful to think about dimension. So the dimension of this higher Lie module is the number of permutations in Sn with cycle type lambda. So you can compute some examples again. If you take lambda to be the partition n, then this higher Lie module will be just Lie n. And if you take it to be the all ones partition, you'll get Hn corresponding to the trivial representation. Okay, so I just wanted to do one quick computation with the regular representation of S3 and these higher Lie modules. So if I did H1 cubed, the 3 partitions of 3 are just the one part 3, and then 2 and 1, and then 1, 1, 1. And if I compute the higher Lie modules, so again, I'm computing symmetric functions here. But Lie3, we saw, I think, way in the beginning, Lie3 was the irreducible index by the partition 2, 1. And then Lie2 was the sign representation. So that's 1, 1, this partition, times Lie1, which is just 1. And then H3 is the trivial representation. So if you multiply this out, you get exactly what you expect for the regular representation of S3. Okay, so now finally I come to the variant that I want to introduce. So this is going to seem a little strange. So I think it was all the more surprising to me that it had these nice properties. So I'm going to let Kn be the highest power of 2 that divides n. And I'm going to define Lie n superscript 2 to be this induced module. So again, it's an irreducible representation of the cyclic group induced up to Sn, but now these are no longer faithful representations of Cn. So it's omega n raised to this highest power of 2 that you see as a factor of n. So if n is 2, then that highest power is 2, so I'm just inducing 1. I get the trivial representation of S2. If n is 3, then there are no factors of 2 in 3, so this power is just 1, right? 2 to the power 0 is just 1. So I get back V3 from Klyachko's theorem. And then if n is 4, again, the highest power is 2, so I'm raising a primitive fourth root of unity to the power 2 squared. I'll get 1 again. Right? So this is the trivial representation induced up. Okay, so from this definition, you can see very easily that there are some properties it shares with Lien. It has dimension n-1 factorial. It's a submodule of the regular representation of Sn, and that's because of the way Sn decomposes into a sum of n modules induced from the cyclic subgroup. Its restriction to Sn-1 is the regular representation. You can see this from characters, or there are many other ways to see it. The character is not value on a permutation sigma is non-zero, only if sigma has all cycles of the same length. Okay. All right, so here are some slightly less obvious observations. Li n superscript 2 is isomorphic to Li n if n is odd. It's the conjugacy action on the class of n cycles, if n is the power of 2. And it's Li n tensored with the sign if n is twice an odd number. So the last one is really the only one that requires a little bit of calculation. I'm going to indiscriminately write Li n or Li n superscript 2 for both the module and its Frobenius characteristic. In fact, I've already been doing that a lot. So again, here's the higher Li module that I defined, but I can also define its variant, which is, it's by replacing H's with E's. Right? I can define E lambda of Li to be almost the same thing, except that I've replaced H's with E's. And of course, I can replace Li with Li superscript 2, which is the sum of all the Li modules. Okay, so here is the first slide. So I'm going to go through this very carefully, so I hope it's not too daunting to look at. So the first theorem is that as a symmetric function, Li n superscript 2 satisfies platistic identities analogous to the ones that Li n satisfies. So on the left, I've listed all the Li identities, and on the right are all the Li superscript 2 identities. And I think I said this before, the classical Li will be in blue, and the variant will always be in pink, or it's actually, I guess, magenta in LaTeX. Okay, so the first one is just, for Li, it's just Thrall's theorem. And for Li sup 2, it's saying something interesting that I'll talk about in a minute. The second one is saying something about platistic inverses of the H, the series of H homogeneous symmetric functions and elementary symmetric functions. The third one is making a statement about what I view as the acyclicity of some complex, or a sequence of modules. Right? You're taking an alternating sum of modules and you're getting 0. And the fourth one, you're adding up these same modules and getting something that I think is interesting. So let's take these apart. All right, so the first one, as I said, this is for Li, this is just Thrall's theorem. It's the decomposition of the regular representation. But let's look at what it says for GLN. It says that the full tensor algebra decomposes as a symmetric algebra over the free Li algebra. So if you interpret it that way, the variant Li superscript 2 apparently gives a GLN decomposition of the full tensor algebra as an exterior algebra over some other object. And this Well, this seems a little weird to me. Um, Again, going back to dimensions, the dimensions of the two pieces, the two higher Lie or higher Lie sup 2 pieces, are the same. It's the number of permutations in Sn with cycle type lambda. Okay. Second property, so this is the one that gives the plathistic inverse of the H's for Lie. This is actually a very old computation of Cadogan, and he got it by looking at graphs and computing cycle indicator functions. But the interesting thing is you can rewrite this, and if you can rewrite this in a friendlier way by taking away this omega of Lie n. And the friendlier way is simply to say that these two series, the series of Lie n and the alternating series of ENs, are plathistic inverses. They're completely equivalent. Okay, so what does Lie superscript 2 say? It's giving you, it leads to the plathistic inverse of the sum of all the elementary symmetric functions, but the equivalent statement is also interesting. I have a pair of plathistic inverses here, the sum of the Lie n superscript 2's and the alternating sum of the homogeneous symmetric functions. Okay, for property 3, which is in the middle of the slide here, right, I need to say a little bit about the partition lattice. So pi n is the lattice of set partitions now of an n element set. And I'll write with subscript r of pi n for the Arth-Whitney homology of pi n. I'm not going to define this, but the reason I'm talking about it is because the Arth-Whitney homology of pi n coincides with the Arth-graded piece of the Orlik-Solomon algebra of the braid matroid of type an-1. I'm not going to define that either, but they're all intimately connected with the Lie representation. So Lehrer and Solomon proved this theorem that as an Sn module, the Whitney homology of the Arth-Whitney homology of the partition lattice tensored with the sign has this Frobenius characteristic. So it's the sum of these E lambda of these, but now you're taking the sum over partitions of n where the length of lambda is n minus r. So there's an annoying sort of backwards shift of indices here. Okay, so what is the dimension of this Arth-Whitney homology module? It's just the signless Stirling number of the first kind. In other words, it's the number of permutations in Sn with exactly n minus r cycles in its disjoint cycle decomposition. So the statement 3, this alternating sum being equal to 0 for Lie, is really asserting that up to sign, that you have Sn equivariant acyclicity of Whitney homology for the partition lattice, or equivalently, of the Orlik-Solomon algebra for type an-1. This is actually true for more than type an-1, this acyclicity condition. What is it saying for Lie superscript 2? So now I'm taking a symmetrized module over this Lie superscript 2, and I'm getting something, an alternating sum that's 0. I don't know. So that's an open question. Okay, and the last property said that the sum of all the E lambda of Lie's was this symmetric function 2e2 h1 to the n minus 2. So for Lie, this is saying that up to sign, if you take the full Orlik-Solomon algebra, or the total Whitney homology of pi n, what you get is twice a permutation module. And this was actually buried, I found it buried in a paper of Gustav Lehrer from 1987, so he knew this. What is it saying for Lie superscript 2? Now I have the sum of all these higher Lie sup 2 modules, and I can write it apparently as a sum of power sum symmetric functions p lambda, where the parts of lambda are all powers of 2. So 1, 2, 4, 8, and so on. So even though, I don't have, as far as I know, there isn't a known context to put this in, there's an interesting consequence. It says that this multiplicity-free sum of power sums, where every part of lambda is a power of 2, is actually Schur positive because it's the Frobenius characteristic of a true module, the sum of higher Lie sub 2 modules. And in fact, it's twice a Schur positive function, just like this one was. So I just wanted to say here that this was actually the start of all these discoveries. My original motivation was I was looking at the character table of Sn and trying to figure out which multiplicity sums of power sums were Schur positive. And so it was a very sort of circuitous route that led to surprising results. Okay, a little more on Whitney homology. So this was actually the reason why I wanted to talk about it earlier. For any poset P, you can define the rth Whitney homology of P. And again, I'm not going to define it, but a long time ago, I showed that if you have a Cohen-Macaulay poset of rank R with a group of automorphisms G, then this alternating sum is a true G module. So it's a fact that Whitney homology is acyclic. So if you took the full alternating sum from top to bottom, you will get 0. But what this is saying is you can truncate it anywhere and you will still get something that's a true G module. So what does this say for Lie and for our E lambda plethism with Lies? It says that this truncated alternating sum is actually a true Sn module. Here's what the dimension is. It's this alternating sum of the signless Stirling numbers. You can check that this always comes out to be something positive. And this module can be described precisely, but I'm not going to do that here. All right, so let's see. So I wanted to look for a counterpart for Lie n superscript 2, so I just mimicked what was happening for Lie n. So I define VH subscript R of n to be the sum of H lambda of Lie n. Oh, this should actually be a Lie sub 2. So now I'm confining myself in the sum, I'm confining myself to partitions of n that have length equal to exactly n minus r. Okay. So for Lie, the analogous thing, if you took the full alternating sum, as I said before, you would get 0. For Lie sub 2, also, the full alternating sum is 0. That was the third property. But in analogy with Lie n, I decided to look at the truncated alternating sums, and I checked this. These truncated alternating sums also turn out to be true Sn modules. They're Schur positive, in other words, and their dimension is the same as before. It's this truncated alternating sum of signless Stirling numbers. I don't know what these are, but it's not hard to show, at least for I less than or equal to 3, that you're always going to get something Schur positive. And here's some data for n equals 6 for these alternating sums. You always get something Schur positive. And for n equals 7. Okay, so this is a conductor. I don't know what the representation actually is or means, but it looks like it's true. Okay, so let me go on to the derived series. So what is this? So any Lie algebra has what's called a derived series, a descending series that you get by taking the Lie algebra L and taking the bracket of any element of L with any other element of L, taking the subalgebra generated by all those bracketings and then repeating that. So it's completely analogous to the derived series for a group, if you remember what that is, with commutator subgroups. So if you write out what the derived series for the free Lie algebra is actually saying, you get something interesting in terms of symmetric functions. I'm going to let kappa be the sum of all the Schur functions corresponding to partitions n-1, 1, starting at 2. So S11 plus S21 plus S31 and so on. And now I want to look at this series of Lies, but with the first Lie 1, the degree 1 term chopped off. I'm throwing that away. Right? So then you can show that this Lie subscript greater than or equal to 2 is this sum of iterated plethisms of this series kappa. Right? So the curious thing is that this fact is also a consequence of the very first plethistic identity involving the Lie representations. Okay, so following what I've been doing in this, in this talk, I'm going to look for a counterpart for Lie superscript 2. So Lie, again, I'm taking all the Lie superscript 2s starting at degree 2 and up and adding them up. And that series turns out to be this sum. It's just omega of those kappas with iterating, with repeated plethisms of them, right? Let me just jump to the last thing. So for Lie, you can show that the degree n term in this alternating sum of plethisms, so now I have a single E n minus r, plethism with Lie 2 plus Lie 3, and so on. This whole thing collapses to one irreducible, the irreducible index by n minus 1, 1, so that's the kappa up here, right? Times a power of minus 1. A similar thing happens for if you do this with Lie superscript 2 and omega of kappas. This time you want to replace E's with H's, right? And then when you take the alternating sum, it all collapses into the irreducible indexed by 2, 1 to the n minus 2. So of course you notice that these are conjugate shapes, but so the sums, the alternating sums end up being conjugate. In other words, they're related by the involution omega. But the individual terms in these sums are not. So in Richard Stanley's talk, something similar came up, if I remember correctly, yesterday. Right? Okay, so here, this actually, on the left side, for the classical blue Lie, this actually comes from an honest-to-goodness Lie algebra fact, the derived series. I don't know what it means on the right side. Okay, next thing that surprised me was a connection with the complex of injective words. So I think I was just sort of randomly reading a lot of papers at this point when I did all this. So what's the complex of injective words? So I take the alphabet from 1 through n, and I form injective words on it. Those are simply words that do not repeat any letters. This forms a poset under subword order. So what is subword order? U is a subword of V. You can get U from V by erasing letters in V. So I only drew P2 because I have a lot of trouble with TXE. Sometimes it can get to be quite a nightmare. But so here's P2. So the words of length 2 are 1, 2, and oops. I don't know how many times I looked at this and missed it. This should be 2, 1. Yikes. And then the words in one letter are 1 and 2. Right? Okay. So so let's see. What do we know about this poset? First of all, it's actually the order complex of a CW complex, the complex of injective words. So that's where this comes from. Uh, ooh, are there, am I missing things in the chat? Sorry. Uh, sorry, I can't really see the chat, so I'll have to look later. Okay, so Frank Farmer showed that this complex has the homotopy type of a wedge of spheres in the top dimension. And then Vic Reiner and Peter Webb came along in 2004 and they computed the SN action on this top homology. This poset actually turns out to be Cohen-Macaulay by work of Björner and Vax, of course. Oops, what happened? Okay, so, all right, so here's the theorem of Reiner and Webb. They showed that the SN homology module satisfies this recurrence, right? So H tilde of Pn is H tilde of Pn minus 1 induced up from Sn minus 1 to Sn, plus or minus one copy of the trivial representation. So, of course, all the experts in the audience who work with permutations all the time immediately recognize the recurrence for the derangement numbers. And indeed, this dimension, this top homology dimension, the Betti number, is the number of derangements, permutations without fixed points in Sn. Okay. So here is the theorem. If I let delta nk be the degree n term in ek, plethism with all the Lie superscript 2's, but starting in degree 2. So you can see derangements coming in there. When I unravel this plethism, I'm not allowing any parts equal to 1 in my partition. So if I do that, and then I define delta n to be the sum of all the delta nk's, right? So this is going to be a finite sum, by the way, because I'm taking the degree n term. Then here's what you can show. You can show that delta n has this explicit Frobenius characteristic expansion in terms of the h's, and it satisfies this recurrence. And of course, if you compare with what's on top, you realize that delta n is actually the Frobenius characteristic of the top homology of the complex of injective words. Okay, so I really don't know why this is happening, except that it is happening. And then I was actually very surprised. Something called the Hodge decomposition of the complex of injective words. And their Hodge decomposition decomposes delta n into a sum like this. So let me tell you what dnk is. dnk is now the degree n term in this plethism, hk with the classical Lies starting at degree 2. So Lie 2 plus Lie 3 and so on. Okay, so I thought at first, all right, this must be the same thing, but it's not. It's not the same decomposition at all. This total sum is the same, but the individual pieces are not. And so here's this first example where they differ for n equals 4. So the top homology of the complex of injective words decomposes into 4 irreducibles like this, and the decomposition coming from Lie sup 2 has 1 irreducible in one piece and the other 3 in the other, whereas the 2 Hodge pieces of Hanlon and Hirsch have 2 irreducibles in each piece. So they're clearly not the same. Okay, let's see, I just want to check how much time I have. Ooh, okay. So another interesting fact about the Lie module is that it lifts to a true module called the Whitehouse module. And the Whitehouse module can be defined this way in terms of Frobenius characteristics. And it looks like the Lie sup 2's also have a lift as long as n is not a power of 2. Okay. So what can we say about the irreducible decomposition in Lie n and Li n sup 2? Well, there's an old result of Folks, and then theorems of Stanley and independently Kraskevich and Weiman that tell us how to do this. And it involves the major index of a standard Young tableau. I think I'm going to zip through this now. So the short story is that we know exactly what the multiplicity of S lambda is in both Li n and Li n superscript 2. It's just a number of Young tableau with major index congruent to something. So we actually know quite a bit about these irreducibles. We can say, thanks to some work of Josh Swanson, we even know which irreducibles will appear in Li n sup 2. This was known for Li n by work of Klyachko already. So we know, for instance, that the sign representation never appears in Li n sup 2, and the trivial representation appears only if n is a power of 2. I think I will skip this because I want to talk about something a little more interesting. Idempotents. So there are these amazing idempotents in the free Lie algebra discovered by Garcia in the late 80s, and before that even by Klyachko that I want to talk about. So first of all, in the group algebra of Sn, I want to define zeta n like this. So omega n, if you remember, is the primitive nth root of unity, and C is the long cycle. Zeta n is just the standard idempotent that generates a left ideal isomorphic to omega n induced from Cn to Sn. The more interesting ones are theta n here. So gamma I is now the I cycle I minus 1 up to 1. So it's a product of 1 minus gamma i's. And so theta n, Garcia calls it the Dynkin idempotent. And kappa n is Klyachko's idempotent. He defined it. So he defined a sum of permutations in Sn weighted by omega n to the major index of the permutation. So in other words, the sum of the descents. So going back a very long way, we know that these are theta n and kappa n are idempotents, and theta n and kappa n actually generate Li n as a left ideal right here. So again, the question is, are there idempotents like this with interesting combinatorial properties for Li n superscript 2? Okay, there are also idempotents for the higher Lie modules. Reutenauer constructed a family of primitive orthogonal idempotents that I'm calling script E of lambda. And then Garcia and Reutenauer showed that this generates a left ideal isomorphic to the higher Lie module H lambda of Lie. So again, you could ask, are there such idempotents for Lie superscript 2? So just to recap, going back to what I said in the beginning about all these different decompositions of the regular representation of Sn, if you decompose into a sum of higher Lie modules, so this is Thrall's original decomposition, you get these correspond to the Reutenauer idempotents. You can conjugate these, so that seems to be a priori a trivial sort of thing to do, but it's actually not. There's the idempotents, these two idempotents are related. These are called the Eulerian idempotents when you conjugate, and they were originally discovered by Gerstenhaber and Schack and Laudet, and Phil Hanlon was the one who made the connection between these Euler idempotents and the higher Lie modules. And then, of course, there are the two different ways to decompose it coming from Lie superscript 2. So I just want to say here, so the way I constructed Lie superscript 2 had to do with using the prime 2. So you could replace 2 with an odd prime, and you know, this would be a perfectly good definition, but you don't get the same kind of results generalizing. So there is something special about Lie sup 2. Um, and my last slide is really a summary slide of all the properties I've been talking about, that where we know pretty much everything about the Lie representation. We know some things about Lie superscript 2, but these are all things that come about with formal symmetric function manipulations. So it would be nice to have a better context for it. So I think I will stop there. Thank you.